Hey everyone, and welcome. Today we're going to do something a little different. We're basically going full on code breaker. We're diving into years and years of big data university exams because we think we found a hidden pattern, a secret code, really, that might just change how you look at the whole field. I mean, just think about it for a second. What if you could actually predict the most important questions on your final exam? Like the core stuff that just shows up again and again. Well, we think we found the key. And believe it or not, it all seems to circle back to one specific question that pops up like clockwork, year after year. Okay, so let's get right into it. After digging through a whole bunch of past exam papers, this theme started to pop out. It was kind of like a ghost in the machine. It turns out that question number 3, specifically, seems to always hit on the 3 absolute cornerstones of the whole big data world. It's like the ultimate test, you know? So this is it. This is the secret code we cracked. The exams are always testing these 3 things. First, the coding style. Second, the processing engine. And third, the storage foundation. And then we'll look at how it all connects. If you get these, you pretty much get the core of everything. So let's break them down. All right, first pillar up, the coding style. This is all about the language you use. It all starts with how you actually write the instructions for the computer. And in the world of big data, the main style, the one that really matters, is called functional programming. And check this out. This is pulled straight from a real exam from just last year. This is a perfect example of a question number 3. See how it's not just asking what functional programming is? It's asking why it's so important. And it specifically tells you to explain pure and impure functions. It's digging deep. So what the heck is it in simple terms? Well, the easiest way to think about it is like a super reliable calculator, right? In functional programming, if you tell a function to add 2 and 2, it will always, without fail, give you back 4. It's not going to mess with other numbers sitting on your desk. It's not going to check the time on the clock. Nope, it just does that one job, perfectly and predictably, every single time. And this slide really breaks down that key difference the exam was asking about. Pure functions, they're your predictable calculator. Impure functions, well, they're a little wilder. Think about a function that tells you the current time. Every time you run it, you're going to get a different answer, right? That's impure. And when it comes to big data, where you're running the same job on maybe thousands of computers at once, you absolutely need that pure predictability. You just can't risk one computer getting a different answer from another. So here's the real takeaway. This coding style, it's the secret sauce that makes massive parallel processing possible. Because these functions are pure and self-contained, you can hand out a million tiny little jobs to a million different computers, and you can be confident that none of them are going to step on each other's toes. That's what makes the whole system manageable and just unbelievably powerful. Okay, so if functional programming is the language you write in, then our second pillar is the engine that actually runs it. This is the workhorse, the machine that takes all those pure functions and executes them at a massive scale. And that engine is the famous MapReduce framework.
And what do you know? Here we go again, another question number 3. This one cuts right to the chase. First, why do we even need this MapReduce thing? And maybe even more important, it asks about handling failures. What happens when one of those thousands of computers just dies right in the middle of a huge job?
Okay, let's break this down with the classic word count example you always see in these exams. Imagine you have a library with millions of books, and your job is to count every single word. The map step is like telling thousands of librarians to each take 1 page, and for every word they see, just write it down with a 1 next to it. So you get the 1, cat 1, and so on. Then the shuffle step is where the system automatically gathers up all the little notes. It puts all the cat notes in one pile, all the notes in another. Finally, the reduce step is when you hand each of those big piles to a new librarian and just say, add up the ones. It's a brilliant way to divide and conquer a huge problem. But that brings us back to the most important part of that exam question, right? What happens if one of our librarians just gets up and goes home sick halfway through their page? Does the whole project just crash and burn? And here's the absolute genius of it. Nope, it doesn't fail. The entire framework is designed for failure. There's a master coordinator, kind of like a project manager, who notices, hey, librarian number 47 hasn't checked in. So it just marks that task as unfinished and hands the exact same page to another librarian who's free. The whole thing just keeps chugging along. That fault tolerance, that resilience, that's what made MapReduce such a total game changer. All right, on to our final pillar. We have the language, we have the engine, but where do you store that gigantic library of books to begin with?
Well, you need a really special kind of file cabinet, and that's a distributed file system, like GFS from Google or HDFS from the Hadoop world.
And surprise, surprise, here's another question number 3. This time it's wrapped in a perfect real-world problem. Let's say YouTube is using a system like this. How on earth does it handle 10,000 people all trying to watch the same viral video at the exact same time without everything just freezing?
So what a distributed file system really does is it takes, hundreds or even thousands of normal off-the-shelf computers, and it magically stitches their hard drives together so they look and act like one single gigantic hard drive. The library analogy works great here too. It's like having one massive library, but it's not in one building. It's got thousands of branches all over, and they're all connected.
And this diagram really shows how it solves that viral video problem. The system has a master node, which is basically a traffic cop. When you and 10,000 other people all request that same video, you don't all hammer the same server. No way. You first ask the master, and it directs traffic. It tells you, okay, you read from server A. It tells the next person, you go to server F, and the next, go to server Z. By doing this, the master itself never becomes the bottleneck, and the whole system can handle a crazy amount of traffic.
So the big secret here, the magic word, is replication. That popular video isn't just stored on one computer. No, it's broken up into big chunks, and each one of those chunks is copied onto several different machines. This is brilliant for 2 reasons. 1, if a machine holding a chunk fails, no big deal. The system just grabs it from another copy. And 2, when thousands of people want to watch it, the system can send them to all those different copies at the same time. The load gets spread out, and no single computer gets crushed.
Okay, so let's tie this all together. Let's look at the complete picture now that we've decoded what question number 3 is really all about.
It all starts with the language, functional programming. That's the safe, predictable way you write your instructions. Then you have the engine, MapReduce. That's the powerful system that executes those instructions across tons of machines and handles any failures along the way.
And holding it all up is the foundation, the distributed file system. That's the super resilient storage that holds all the data your engine is working on. And that is the ultimate takeaway. The reason these 3 things show up in question number 3 over and over again is that they aren't just 3 separate topics. They're one single integrated system. The language, the engine, and the foundation, they're all designed to work together to solve the enormous challenge of processing massive, massive amounts of data.
So there you have it. We've cracked the code for the classic era of big data. But it kind of makes you wonder, right? With technology always moving forward, think about real-time streaming or AI. What are the new pillars? What's going to be the question number 3 of tomorrow for the next generation of engineers? Definitely something to chew on. Thanks so much for tuning in.